I'd like to introduce Professor John J. Leonard, Professor of Mechanical and Ocean Engineering and Associate Department Head for Research in the MIT Department of Mechanical Engineering. Please give him a round of applause.
Hi, everyone. Thanks for having me here. It's a great pleasure to talk to so many young people that are excited about robots. I've just obsessed with robots and how mobile robots can navigate and build maps and go through the world. And so in this talk, I want to just give you a little glimpse into life of research at a place like Michigan or MIT, and talk also about self-driving vehicles and some of the challenges they face, and some of the sort of coverage that's been in the media, and how that reflects back against some of the algorithms that that we work on in robotics research. In this slide, I have a couple videos. One is of our DARPA Challenge autonomous vehicle from the DARPA Urban Challenge that I was the team leader for at MIT. And that's on the left, and on the right is a research robot going around in our building at MIT in our computer science lab that's making a map and using the map to navigate. And that's the kind of algorithms that I work on. So first I wanted to ask you a sort of news quiz. Does anyone recognize this car? Does anyone know what this car did in the last few weeks? Any young folks? Okay, so this car crossed the US, quote, autonomously, and we'll come back and decide what that means. And this is by Delphi. So this is actually from an article in Wired. This is big. A robocar just drove across the country by a writer there, Alex Davies. And a quote here that the car took 9 days to drive across the country. So actually here's, they started in San Francisco at the Golden Gate Bridge. They took a southerly route to avoid some of the weather that we get up north. And they did it in 9 days. And the car did 99% of the driving. And this is a pretty good snapshot of where we are now. And I was asked in the media about this, what did I think? And I said, well, it depends if you think the glass is 99% full or 1% empty. And so I want to convey my excitement and enthusiasm for robotics in general and self-driving cars in particular. But I also want to convey a picture that there are great challenges to be solved. And if anyone tells you this is a solved problem, you can tell them there's at least one MIT professor that disagrees with them. And for the young generation, there's a lot of great research to be done. So I've worked in robot navigation my whole career. I was an undergrad. I grew up in Philadelphia. I went to University of Pennsylvania. And I got the chance to work at a General Motors factory in Wilmington, Delaware, the summers after my sophomore and junior year of college. And so I worked on part of the plant maintenance team where they built if anyone older remembers, the Chevy Beretta and the Chevy Corsica. We renovated the entire plant to put in robots. And I really got to see what it was like in a car factory. It was just an amazing experience. And there when they rebuilt the plant, they had to pour new concrete floors with wires in the ground for the robots to follow with a magnetic sensor wires buried in the concrete. And this wasn't very flexible. They spent millions of dollars, $300 million redoing the plant. And so when I got the chance to go to graduate school at Oxford, it was an amazing, I really feel like I've won the lottery in life. If you work in science and technology and you work hard, there are so many benefits that can accrue. I'm really fortunate to have worked with amazing people in amazing places. I got to go to Oxford for my PhD in England, and I could sort of write my own ticket for what I wanted to do. And I said, well, those robots that had to follow wires in the concrete, what if they could navigate based on the environment by building maps and using those maps to navigate? And that's what I worked on. And then after I graduated with my PhD, I wanted to come back to the States. And I had a PhD from Oxford. I was on top of the world. I couldn't find a job. I got the chance to work in an underwater vehicle lab at MIT as a postdoc. So I started working on robots going in the ocean and got to do some amazing things like go to the Arctic and write software for a robot that if we put it in the ocean, I was told if we lost the robot, I would lose my job. And it's real easy to lose a robot in the ocean, you can ask Professor Eustace here at Michigan is an expert in underwater robotics. So anyway, I joined the faculty in '96, and one of the great adventures of my MIT career was to be the team leader for this thing called the DARPA Urban Challenge in 2006 and 2007. And we had, I'll play some videos for how our robot worked. We had a big team with 3 or 4 other faculty co-leaders, some amazing students. One of them, Ed Olson, is now a professor here at UMichigan. He'd be here today, but he's in sabbatical, on sabbatical in Europe. And we tried to build a vehicle that navigated more using its perception than blindly following GPS. Because GPS has problems. It can be, you can get interference near buildings, you can get all sorts of errors. And in a nutshell, for a robot to navigate, the real challenge is dealing with uncertainty. When the robot's sensors make measurements of the world, they're uncertain and ambiguous. And when the robot moves, you give commands to the wheels and the steering, the motion isn't exactly what you want. There's little bits of error, and that error grows with time. So our vehicle, so shown here in the lower left, is a sensor called a Velodyne scanner. There happens to be a Velodyne in the back of the room. Check it out if you get a chance. This one gives 1 million data points a second. This is for driving up a place called Mass Ave from MIT to Harvard. And even though with our eyes we can see buildings and cars and people, for a robot to try to interpret that data is really challenging. And then over here on the lower right, you can see we created a system that tried to use vision and lasers to follow the road instead of using a prior map. And that had to deal with looking into the sun and shadows and all sorts of errors and challenges. And in the upper right shows the video of our perception and planning system. So one of the real challenges with robots is closing the loop. When you make it autonomous, it has to make a decision about how to move through the world, and doing this in real time in the face of all this uncertainty. So we used a very researchy algorithm for a robot to plan its paths. And so in fact, if anyone here has anyone heard of the KISS principle? Keep it simple, stupid. At MIT, my colleagues did not want to follow this. They wanted, and there's another thing, the not invented here syndrome. Our students, especially Ed, who's a professor now at Michigan, he wanted to write all new software for the vehicle. So in just a year and a half, we wrote 150,000 lines of software. And when we built our vehicle, my colleague, Seth Teller, he didn't want to be limited by the computers we could fit on the vehicle. So we got a blade cluster, which it was a lot at the time, 40 cores. It required 3.5 kilowatts to power the computer. We had a 2-kilowatt air conditioner on the roof to cool the blade cluster. And we had more sensors than any other team. And our vehicle, and we wanted all this computation because we wanted the car to sort of think. We wanted it to perceive the world and use that to navigate. So at the end of the day, the competition, it was $2 million for first place, $1 million for second place, $500,000 for third place, nothing for fourth place. We came in fourth place. But, and the teams that won, Carnegie Mellon and Stanford in particular, did amazing work. And their technical team leaders, 2 people that should be very famous to roboticists, Chris Urmson. Does anyone know what Chris Urmson's up to now? He's the leader of the Google self-driving car team. He led the Carnegie Mellon team. And Mike Montemerlo is like the key mapping and localization guru of the Google team. And he led the Stanford team, along with Sebastian Thrun. And just some of the videos I have sound. So if we try to switch now to the other display and play this video, if we can. And if it doesn't work, we'll just do it without sound. Go back one. Play this one first, and raise the sound. So,
the U.S. government has challenged the civilian robotics community to create a car that can drive itself.
This is just about the hardest thing you could do to an autonomous vehicle.
Despite the long odds of winning, more than 80 teams have jumped at the chance.
The biggest challenge is dealing with the unexpected.
For the elite few who reach the finals, a $2 million prize is at stake. Which robocar will be first to the future?
When robot meets robot, no one really knows what's going to happen.
Unfasten your seatbelt and get out of the car. The roughest race without drivers is about to begin.
Okay. So go to the next video. Don't press play yet. I'll set it up. Yep. So even though it was an autonomous race, one of the sort of secrets about robotics research is a lot of times the robots don't quite do 100% of the job. People need to intervene and fix things when things go wrong. Like the Delphi trip across the country, 50 miles were manually driven. And there were things like tricky interchanges, getting on and off the highway, parking lots. And so for things like highway driving with good weather, things are really well understood. But it's handling the unexpected events that happens. And so in the DARPA challenge, even though we finished the race, we actually had a few incidents along the way. And one of the famous ones was with our incident with Cornell. So I'll explain what happened in a minute, but if you can press play on this. And the announcers here are the guys from Mythbusters.
All right, let's check in once again with the boss, Tartan Racing. Remember, they were the second vehicle to cross the line at the end of Mission 2 behind Virginia Tech. Virginia Tech, whoop, there we go, got a little issue.
Here's 26 Cornell. Looks like they're stopped.
And it looks like they're, the 79 is trying to pass and has passed the chase vehicle for Skynet, the 26 vehicle.
Wow.
And now he's going to, and Talos is going to pass.
Very aggressive. And
Whoa! Oh, we had our first collision. Crash in turn 1.
Oh boy. That is, that's a bold maneuver for MIT to try and pass. And I'm sure
Okay, do you want to come back to my machine? Okay, so most MIT professors don't advertise their failures like that, but I think it's important to have a conversation with the public and with the media about what some of the real challenges are in robotics, and things always don't go as you like. And I think in general in life, don't be, like everyone will have setbacks and failures and you have to move on. And in fact, it was our research-driven strategy that led our vehicle to have these sort of unpredictable things. So it turns out with an autonomous car, you can get really good data recording to figure out what actually happened. So in this video here, we can get a little look inside the brain of the car, so to speak. And so I'll pause it in a second. So what's going on here is we can see the 3 cameras looking out the front of the car and then the vehicle's internal map. And even though the road was really wide there, the prior map that we had to follow had just a single lane. This was going back to the start-finish area where DARPA were going to give us new missions during the race. It was broken into 3 parts. And even though with our eyes we can see that's a car, we see license plate, taillights, number on the back. Of course that's a car. Stay away from it. To our algorithm, it was just a blob of laser scanner data. And we weren't smart enough at that point to do the classification that that's a vehicle. This is actually something that Google are really good at now, so classifying cars, pedestrians, cyclists. And so our planner planned a very aggressive path around the car, thinking it was a stationary object. And so as we play the video, it turns out that Cornell had about 5 bugs, and we had about 5 bugs that interacted to cause the collision to happen. And Ed Olson's not here, so but I did want to show. This is one of the pictures. This was actually 2 or 3 days before the race. It was Halloween, so the race was November 3rd. The students put a pumpkin on top of the car. And a lot of my time was spent sitting in the back seat. So this is actually Professor Olson, if anyone knows him, from Michigan. And that's one of our postdocs in the front. He was looking at a computer screen. Ed was looking at a computer screen. And I had my head in my hands, either from exhaustion or stress or both. And it turned out that in our code, in all the software we've written, and I'm sorry for showing you code, but this is, Ed had this, if the velocity of an object is greater than 3 meters per second, and it's been around for 8 time steps, then we're going to call it a car, basically, is what that says, translating the code. And all these systems have thresholds. There are things called receiver operating characteristic curves. And real systems, it takes years of training and data to get the reliability that you need. So, for example, I see Jeff Rupp from Ford here in the audience, and I'm sure he tested for years active safety systems where you need to get 99.99999% reliability to turn something loose to the public. And unless a human can step in and take control, it's really hard to get that level of reliability. Now, we actually wrote a journal article with Cornell where we published the data from this and other incidents as like a learning experience. And we also published how our lane finder worked. We had a wonderful PhD thesis. We also made major advances in motion planning. And so even though we chose a more research-driven strategy, as a professor, my first goal is educating young people to go out there in the world and to do great theses. And so as a research project, even though we were 4th place, it was a great success. And so here's an example. Our student, Albert Huang, created this perception-driven navigation system. It could navigate between waypoints as far as 200 meters away, finding its way along the path in real time. So the sort of research we do, we want to make it so that robots don't need precision a priori maps or very expensive sensors, but they navigate a bit more like people or animals navigate. And there's some deep questions there about how you represent the world, how you deal with uncertainty, how you develop efficient algorithms. And let's see. So this was in 2007, and if you asked me at that time, I would have said we're a pretty long way from a car that could drive, say, in downtown Boston 100% of the time reliably. And but then Google surprised us. So in 2009, Google hired some of the best engineers from the DARPA Urban Challenge teams, Urmson, Montemirlo, others, and they developed the Google self-driving car. And that project just jolted the entire industry. And it's really amazing for me to look back. The project was secret in the first year, and it was publicly announced in October 2010. A New York Times reporter, John Markoff, sort of discovered them and threatened to out them if they didn't cooperate. And when Google were doing their initial testing, they had this rotating scanner on the roof, and people would come up to them and say, "What are you doing?" And they said, "Oh, it's a UFO detector." You know, and they sort of kept secret that they were testing. And the whole question of regulation, and there's a lot of deep questions here about how you do it. Now, but I did get the pleasure this summer to give a talk at Google and have a ride in the Google self-driving car, and it was just amazing. Like, I posted on Facebook, I felt like I was on the beach at Kitty Hawk. You know, the performance of the car was flawless. This is me and one of my students, Ross, who's an MIT PhD student who got to come along. And so while I'm a big fan of the technology, and I'm so excited that all this technology is getting into, for example, active safety systems for cars, there are a lot of questions. And so mostly I focus on the technological questions, but the implications for the economy, for employment, the ethics, legal, insurance, security, there's a lot of big questions here. And I think we want to have a good conversation about what might happen next, but also to make it technologically based. So in the next part of my talk, I'm going to adopt a little bit of a devil's advocate position, and I don't mean that to dampen any enthusiasm for the excitement, but just to try to inject some of the questions I think about, things that keep me awake at night. And so, let's see. I apologize for so many words on some of these slides, so for the young people, don't copy this. But I was interviewed back in July of 2013 by MIT Tech Review. A reporter sticks a recording thing on the table and just talk for an hour. And I'm sure I raved about how amazing Google were and how much fun it was and so forth. But they pick out 3 or 4 sound bites, and they use that in their article. And one of the things I said is that there are major unsolved difficult issues here. We have to be careful we don't overhype how well it works. Now, at this time, I had never heard of this thing called Reddit. Who's heard of Reddit? It turns out there's a self-driving cars page on Reddit. And I was Googling this article, like to send it to my mom or something, and I found this page, a test drive of the most advanced driverless vehicles. So on Reddit, they post any article to do with self-driving vehicles, and then they make comments. So one of the things I said was that I do not expect there to be fully driverless taxis in Manhattan in my lifetime. And this person wrote, "Talk about a Debbie Downer, he's not even 50 years old." Okay. And then someone else wrote, sounds more like someone that's afraid of the technology and has trust issues with machines. But I do have trust issues with machines. It's really my job. In fact, I brought 2 laptops because I mistrust PowerPoint so much. So when I saw this, I got a dash cam, and I'm so obsessed with mobile robots that I think all the time about robotics. When I'm on an airplane, I think about remotely, autonomous airplanes. And when I'm commuting in Boston, I think about, could a robot handle this situation? Could a robot handle that situation? So I started recording my commuting in Boston. And so I had been recording for about 5 minutes. So for about 3 weeks, I recorded going back and forth from MIT in Cambridge, Mass. to a place called Newton, about 9 miles away where I live. And after about 5 or 10 minutes of recording data, this was my first situation. So we have a red light, and there's some sound here, but you won't hear it, but don't worry about that. So pedestrians running out, when the light turns green. Maybe that one would be pretty good. And in fact, computer vision technology has made huge strides. For example, there's something called deep learning, which is really leading to major advances in things like recognizing objects and visual data. But in the course of collecting data, I did find some tricky situations. And this first video, this is not a dash cam. I actually had I was taking my oldest son to middle school, and I had one of his friends use my cell phone to record this tricky intersection, and that's making a left turn. So has anyone here learned to drive recently or hoping to learn to drive soon? Have you had a chance, for example, with a parent about making a left turn where you have to make that go-no decision, like safe, not safe? And so this one is, first of all, there's snow on the ground. We'll come back and talk to snow. But if you look to the right, there's a lot of traffic. There's cars as far as the eye can see. If you look to the left, there's cars coming at quite high speed. And there's a mailbox and a tree that's occluding things. And also the snow on the ground confounds the way the car positions itself. And the only way I could pull out at this intersection, because we have such bad traffic in Boston, is to wave at another driver and sort of like have a little courage and pull my car out. And that's sort of those nods and winks that you do at someone. And so John Markoff from the New York Times posted this on the Bits blog of the Times, and he called it the social ballet of driving. And so even though 99% of driving can be automated, things like left turns without a traffic light often require the sort of subtle human communication, which are some of the most challenging problems of human-robot interaction I can think of. Here's another one. So this is, I'll play the longer version in a second. Light's green, there's a police officer there, and he just sticks his hand out. And even though the light's green, the car has to be smart enough to know that's a police officer, they're putting their hand out, and pedestrians are going to cross. Now, some other situations that are hard, in particular, given how the Google car works, is if the road surface gets repaved, or if there's snow on the ground. And even just a light covering of snow could confound the navigation. Here's another, the longer version of that police officer sequence. So there's a flashing lights, which are very hard to deal with and interpret. One officer waving me through a red light, and then the next you just saw is an officer stopping me at a green light. So to really drive in downtown Boston, downtown Manhattan, some of the perceptual challenges, and it's almost a sort of general purpose common sense intelligence that we have about how to parse highly dynamic scenes and how to respond to people. And some of those problems are just deeply hard computer vision problems. And so that's why I believe it might be a very long time, maybe 15 years, maybe I was too pessimistic to say not in my life, but to truly turn a robot loose in Manhattan with no human intervention, it may just be too hard. Now, here's another one. So does green always mean go? So the light's red, and we just wait a bit. So the cop was waving me through and then just turned his hand like that. And that's enough. So the MBTA trolley had just arrived, and people always get a little crazy when the trolley arrives, especially when it's cold. They all sort of run through the traffic to get it. And another thing is the whole issue of sensing. So the laser scanners are great, but they cost $75,000. Now they might be made a lot cheaper, but that's a pretty expensive option on a car, at least today, and not to mention the aesthetics. Now, there's been great strides in computer vision, but you do have to deal with things like looking into the sun. So what do you see in this picture? Anyone see the sun? Anyone see a traffic light? Anyone see the police officer standing right here? There's a police officer right here. These are the shadows of his legs. So one of the challenges when you turn a robot loose in the world is maybe the sun is difficult. Maybe busy intersections are difficult. Maybe traffic cops are difficult. But you don't know if you deploy this at scale with millions of vehicles, they're all going to happen at once. And how do you test that? And not to mention snow. Now, of course, there's the difficulties in traction and that sort of thing. But what I want to try to do, without getting too technical, is to dive down a little deeper and talk about how robots navigate and how the Google car actually works. And so if you cover the road surface, that removes the way in which many self-driving cars achieve precision navigation. So this is a little, if you want to know how the Google car works, they don't really publish academic papers. They have a ton of patents, and they've also given some great technical talks online. So if you Google something called the Solve for X conference, one of their core programmers, Dave Ferguson, gave a fantastic talk in which he says how the car worked. And the lowest level is how you automate the car, so making it drive by wire, adding computers and sensors. And the next level is called mapping and localization. And what Google do is they map the world very precisely, the appearance of the laser scanner data in the world, and I'll show that in a second in a video. And they do that in advance, and then humans fix the map, annotate the map, add traffic lights, add crosswalks. And then when they're actually driving the car, they match the way the road should look to the laser scanner to the prior map, and that gets them 10-centimeter accuracy. With just an ordinary GPS from your phone, you'd be lucky to get a couple meters accuracy. That's not enough to not be driving in the wrong lane. So here's a little excerpt from one of your Google videos about how their car works. Sorry for this. And so here you can see the map that they make. And so that grayscale that you see is how the laser scanner reflects off the ground. And it's an amazingly robust algorithm when the world matches the map. So what Google have really shown is if you have a good map, you can predict what the robot should see, and if you know your position, then you can simplify the problem of dealing with the unexpected. And so when I said that I felt like I was on the beach at Kitty Hawk, I make the analogy with the Wright brothers. The key thing the Wright brothers did, does anyone know? I wish we had. What was the key thing, the key idea that the Wright brothers came up with that caused the breakthrough? Yes, with the red t-shirt. Well, they had airfoils to generate lift. They needed three things, so very good. They used airfoils, which they tested, as the previous panel mentioned, without people in them. Good. The second thing they needed, anyone? It's louder? Yeah, they needed a big flat space, but what's that? Control. So let's say number 2 was a lightweight engine, so force. But the real breakthrough was control from this gentleman in the front here. They came up with a clever strategy to decouple the control of the pitch from the control of the yaw and the rudder, yaw and the roll. And that decoupling let Kitty Hawk happen. And so instead of making an inherently stable aircraft that could fly, they made an unstable aircraft and had a clever control algorithm for stabilizing it with continual human feedback. And in the same way, the Google car does this decoupling of what it should expect from its map to handle the expected, and that lets them classify the unexpected, things like pedestrians, cyclists, and that's how they get such good performance. So, but the catch is that if you can't see the ground, then that doesn't work. So in general, what we're doing in our research is how robots might navigate based more on objects in the world and having more perceptual understanding of the world. And I just feel that we're many PhD theses away from that level of understanding. So I don't know if there's, so I would normally ask for questions, but I want to keep you from lunch. I'm going to try to now give like 10 minutes, a little window into some of our research, some of the things we work on. And so I mentioned about making the map, and The problem I've dedicated my life to is a thing we call simultaneous localization and mapping. And this is how a robot makes a map and concurrently navigates with the map. So this is an example, sort of famous in our research community, of it's actually a pickup truck driving around a park in Australia, in Sydney, making measurements of trees with a laser scanner. And the blue path is what we call the dead reckoning. And so the dead reckoning position of a robot, the error grows without bounds. It gets more and more lost. And what the SLAM does is, by estimating some landmarks or some features in the world, you concurrently map their locations and stop the dead reckoning error from accumulating. And one of the challenges, this is from Professor Olson's thesis, is navigating around the corridors of MIT, is when you do a loop. So we have a problem we call loop closing, is when you travel in a big loop and you come back. So this is actually 2 hours of a robot slowly navigated around the halls of MIT. And by matching the laser scans one to the other, you get a kind of a more accurate dead reckoning, but the error still grows. Now watch right now. Now what happened? We applied constraints so that if you know you came back to where you started, you can take out the dead reckoning error and make a more accurate map. And here's the video I showed earlier on my title slide, where using 3D vision data to make 3D maps. And so using either stereo, or there's the sensor, the Microsoft Kinect, we use a lot. And here the robot's navigating around, and it's gradually introducing errors, but it corrects them. So you see this sort of corridor doesn't line up, and then it gets sort of shoved into place. Now, if you want to work on like the algorithms that underlie this, you need to be really good at programming, and you need to be good at math. So perhaps in high school you might have done fitting data to a line segment. And usually you use a least squares objective function. Like you say, you want to minimize the sum of the squares of the errors of the data points with your line. And that's basically what we're doing. It was developed by Gauss over 200 years ago. Least squares estimation. We're just doing it really big scale, and lots of other things thrown in. And one of the challenges is dealing with the three-dimensional world. So the Google Cars effectively makes a 2D map of what the surface looks like. But for things like drones flying around inspecting bridges and just true 3D complex environments like a taxi in downtown Manhattan, I believe we need full 3D mapping. And this gets really challenging. So here's an example, some work with some collaborators in Ireland. My wife's Irish, and I work with some folks in Ireland. We're doing what we call dense mapping. So we're riding on the coattails of video game technology using GPUs, which enable like really fast parallel processing of big amounts of data. And this is walking around an apartment in Ireland, and in real time you can make a 3D map, and I'll show you in a second. Actually, here's that same video playing again. So it's getting sped up by 16, and just walking around, and there is this gradual increase in error, but the algorithm corrects it. And at the end, you'll see, like, look for example, in the bathroom, like the quality of the resolution of like the tub and the sink. We can really build rich 3D models now. And the hope is that we can, on top of that, be able to classify objects and then be able to use that to navigate accurately in the world. So here's a little example of the kind of, this is a few years old now. What we've done since then is add in the loop closing, and I think I'll show one of those in a second. Now, you've all probably seen scanning people, like there are scanning stations where you can go in and multiple sensors will scan you. Showing you the sort of thing we can do. This is, we can scan people. These are my collaborators, and make like models of people. So imagine if you could use your mobile phone and you could scan yourself in and then insert yourself in your favorite video game. So if you had like, a soccer video game, and you could have, you and your high school friends playing soccer with like famous soccer stars. That sort of thing is all coming, in terms of 3D perception of the world. When we build the model, we build a volumetric representation of space, and if we make the model very small, we can get very high accuracy, but that limits where we're processing. But to show you how accurate we can get a model, this is just a scan, 30 seconds of data of one of my collaborators' faces. And when I show this, my wife, who I've known since 1993, she's been an incredible supporter of my career, But back in the early days, we used to assume the world was two-dimensional, and the robot would make, like the video I showed earlier of the loop closing, and she said the real world is three-dimensional. The robot is going to fall down the stairs, you know, and this is the first result that impressed my wife. She said, now I think what you're doing might actually be useful. So it's how you combine data from multiple vantage points to get more accurate models. So here's an example of taking the dense mapping combined with the loop closing, where we, like, imagine if you could map big complex buildings and build rich, detailed 3D models. So here's an example. If you saw those two blue chairs that were misaligned from the Dead Reckoning, and here's a little fly through the model. So I want to make like a virtual fish tank for all of MIT. I can fill it with water, and you could just sort of swim through and take a tour and have like this rich 3D representation of the whole building. This is just a small step in that direction. So here's an example of maps we make, like walking around with a sensor. Let's see. So I also want to mention a couple other exciting robots we have at MIT before I wrap up. So I have a wonderful colleague, Russ Tedrake, is leading something called the MIT DARPA Robotics Challenge team. So it's called the DRC. It's the next big robotics challenge that DARPA has organized. The finals are happening this summer, and they're using humanoid robots to do disaster response tasks. And so MIT is one of the teams with what's called an Atlas robot built by Boston Dynamics, who were acquired by Google a little over a year ago. And one of the things that they've done with it, so I had this amazing postdoc, Mars Fallon, who's now a faculty member in Edinburgh University, and he worked on taking the dense 3D mapping I showed you, like mapping the person's face, and using it to map 3D terrain in real time so that the Atlas robot, without any prior information or motion capture system, could sense obstacles on the ground and then plan its footsteps to walk autonomously over the steps. So this is sort of the state of the art today. It's a little fingers crossed. They have a crane overhead. Like, for example, the robot fell once by mistake and it broke its arm off and it had to get it replaced, and it took a month. You know, so, but it's very exciting that we're getting 3D perception to enable advanced interaction with the world. And one more of my favorite robots. I have amazing junior colleagues at MIT. This is Professor Sangbei Kim. He's built a robotic cheetah. And this is pretty cool with the sound, but we'll just play it from here without the sound. He's enabled it to jump over obstacles. So it uses perception to sense the obstacle and then a fancy control algorithm to try to compute the inputs. And so he's having this running around campus a bit. So a lot of the innovation comes in the design of how you use motors in a way that sometimes they're powerful and rigid, and sometimes they're soft and compliant. And here's one more cheetah video. So Boston Dynamics also have a robotic quadruped. Since Google bought them, they've gone a little more secretive. We don't know what they're working on. But it's certainly fun when we're showing people around to show them the cheetah. So so we're collaborating on how we would put our perception onto the cheetah so that, for example, it might be able to run through the woods. Now, I also have collaborators. I didn't put the video. I got it. I do have it in. No, I don't have it in here. I have a collaborator, Nicholas Roy, who works on drones. He took a 2-year leave from MIT to work on something called Google Project Wing, if anyone heard of that. So they made a package delivery robot that flies and is a tail-sitting configuration. And they delivered some dog biscuits in Queensland, Australia. They had to do their tests in Australia because they couldn't do it legally in the US. Let's see. So I'm going to wrap up because it's pretty much time to finish. And I thought I'd go back to the self-driving car theme. And so I am very excited about the technology, but I do want to convey that there's a lot of great research to be done, and there's a lot of work for the young generation to do. The problems are not all solved. And some of the key challenges, in my view, are maintaining maps, dealing with adverse weather, interacting with people, and building better sensors and have a better sensor processing algorithms. And one other wild card that the automotive folks would know about is there's a technology called V2V and V2X, vehicle-to-vehicle and vehicle-to-infrastructure communications, where cars might be able to talk to each other. And so instead of me waving at this person to say, please let me in, the cars could communicate with themselves. In fact, sometimes I've speculated, like for Boston, because the drivers are so uncooperative, that we might create a sort of economic system where my car would automatically give another car 5 cents or 10 cents if they're nice to me and let me in. Or maybe they would penalize them 25 cents if they're mean and they cut me off. You know, so some sort of, but there might be a way with technology. And in terms of interacting with people, there are two different approaches to developing autonomous cars that are dominant. And there are these levels of autonomy that NHTSA has defined. So levels 1 through 4. Level 3 automation is where the car does almost all the work, but you have to pay attention and be ready to take over if something goes wrong. And that's a typical active safety system today, for example, what Delphi demonstrated. A level 4 car would be so good and so reliable that you could go to sleep, or you could just read a book, and the car will safely get you from A to B. And one of the challenges with, do I have a few more minutes for a fun video or two, or should I stop? Let me just show you, if you need the human in the loop, part of the challenge is getting the human to pay attention. So there are some videos posted on the Reddit page that I really like. This is a famous one now. It's called the soda can video. Has anyone seen this? So BMW, for their autonomous lane keeping system with adaptive cruise control, you need your hands on the wheel, and if after 10 or 15 seconds you take your hands off the wheel, the system will disengage. It wants you to pay attention. Someone figured out you could hang a soda can on the wheel, and it generates just enough downward force that the car thinks you're holding onto the wheel. All right? So, and then in this video, the car just drives. This is a German motorway, Autobahn. But then, not to be outdone, someone figured out that the Infinity does not need you to keep your hands on the wheel. So there's this video. It has this wonderful Wagner soundtrack that you can't hear. But they're just driving along for minutes at a time with no hands on the wheel. And then I call this humans will do stupid things. And you'll see that in a moment. So I'll jump to the end of the video. So what they say is, nice, no hands required, not even a soda can. Now let's try something. Just watch this for a second. So I do not recommend this, and this is one of the challenges, is people need to learn how to interact with autonomous systems safely. Now, the way these systems work is if you touch the wheel, it disengages. So at the end of the video, it says, just be careful not to hit the steering wheel. The person climbs back in, their butt hits the steering wheel, the system disengages, and the video goes blank. So we don't know what happened. Let's see. But I'd like to close with this video, which is more, so my prediction of the near-term future is that we're going to need drivers to pay attention. And we need to train people to understand the shortcomings of autonomous systems, take advantage of what they can do, but then be ready to, the autonomous system should be ready to jump in. And so I don't know if anyone's at this one would be great with sound. Let's see if I can get the sound. This is my favorite commercial. It's from Super Bowl 2014. And as a father of 3 boys, I'm playing this. So let's see if this works. I gotcha. Oh, you can't count on me. 1, 2, 3, I'll be
Remember when only Dad could save the day? Sorry. Auto emergency braking on the all-new Genesis from Hyundai.
So that's what I think we need. I think we need to keep pushing the technology. We need to educate people about how to interact with these systems. But I think we can achieve a statistically significant reduction in accidents and injuries by technology that can jump in and save the day when an accident might happen. So thanks for your attention.